want to conclude with just a few more examples and some cautions about correlation and regression. Okay, so correlation we talked about was for linear relationships. If you had a curved shape or a periodic shape or something, there might be a better model, but correlation measures how linear the relationship is. Regression, at least right now, we're looking at linear regression. You can do other types of regression, but we're looking at linear regression in this section, in this class. That's the one type of regression that we look at. Both of them are affected by outliers, as we just looked at, and we saw that correlation is greatly affected by outliers. So always plot your data before making an interpretation. You might get a really strong correlation and think you have a strong linear relationship, but you look and see that it's really just because you have one outlier that's causing that. Okay? So always make sure you look at your data before you make an interpretation. Okay? And then two things we're going to look at examples of here. You got to watch out for extrapolation. Okay? When you take a linear regression line, you can use it to predict the y values, predict your y hats using the x values. If you take and you make predictions for x values that are way outside the range of the data you started with, that's called extrapolation, and often it is inaccurate. Sometimes it's physically impossible when we look at it. You also got to look out for lurking variables. We're going to talk later about good ways to do random sampling and set up experiments, which helps you counter the effect of possible lurking variables. But a lot of times, two variables you're looking at are actually related to other variables that influence what's going on, okay, and can give you misleading results in your interpretation if you're not careful. That kind of goes along with the fact that correlation does not imply causation. You can have something be very strongly correlated, but it's not that one is causing the other. So extrapolation, here's a pretty common example. Think about somebody's height or their weight. Over time, eventually you have to stop growing, right? So Sarah's height was plotted against her age, and we have a plot over here where we have her age in months and then her height. When you're young, you grow at a relatively linear rate over a certain period of time. Can you predict her height at age of 42 months? Well, yes, you can pretty accurately according to the data here. So you have your linear regression line. If you made your prediction, you'd go out to 42 and find the y value, which would be 80 something there, about 87, 88, something like that. I'll have the actual numbers here in a minute, but that would be what's called interpolation, and looks like it's pretty accurate. Okay? But extrapolation, can you predict her height at 30 years, age of 30 years, 360 months? No, that's going to be extrapolation. My data only goes up to 60 months. If I go way, way beyond that to 360 months, that's by definition extrapolation, which is usually not accurate, and here definitely not. She's not going to keep growing forever. Okay? I have here the actual equation. If you took the data and you found the actual linear regression, y hat's 71.95 plus 0.383x, and if you plug in 42, you get 88 centimeters, which was reasonable. But if you plug in 360 months or 30 years, you get 209.8 centimeters, which converts to nearly 6'11", 6 foot 10 and a half inches, which is probably pretty unreasonable for a woman, right? So that's an idea of extrapolation. Anytime you go too far off in the x direction, it's called extrapolation, and it's probably inaccurate, and a lot of times becomes physically just kind of ridiculous when you look at it. Here's an example of a lurking variable. And there's always, that's why we need to do good experiments. There's always so many lurking variables we can't possibly think of, but here's an example that I had in a textbook one time. So young children who sleep with the light on are much more likely to develop myopia, which is the fancy word for nearsightedness, later in life. Okay? So that statement, the former, is a recent scientific example, not so recent anymore if we look at the date here, but from 1999. It was an example that was published by the University of Pennsylvania Medical Center, which is, is an Ivy League university, their medical center, very well respected. And they published that in the magazine Nature. The study received much coverage at the time in the popular press. So people started thinking young children who sleep with the light on are much more likely to develop myopia. Is sleeping with the light on causing nearsightedness? Well, a later study at Ohio State University found that infants sleeping with the light on did not cause the development of myopia, but there was a strong link between parental myopia and the development of child myopia, and the nearsighted parents were more likely to leave the light on. So a lot of words there, a lot of rambling there, I guess. But there's this lurking variable. There's this strong correlation between having the light on and the children becoming nearsighted, but the lurking variable that explains it is genetics. The nearsighted parents, they needed the light, and they had nearsighted children. Here's another example, kind of meant to be sort of I don't know if you'd say it's humorous example, with fires causing a lot of damage. I guess is not humorous, but just kind of a silly example. The number of firefighters present at a fire has a strong positive correlation with the amount of damage. So can you say that firefighters cause damage? Now that one, it's, like I say, that's kind of the ridiculous assumption. It's probably in the other direction, right? Having more firefighters are there because there's a worse fire that's already causing more damage. So just some advice on causation. We want to show causation a lot of times, but the only good way to do that is with randomized experiments that we'll talk about later in this class. If you can't do that, then some things to look for. The stronger the association, the better the evidence. The more consistent it is. If you can repeat it over and over in different trials and keep getting the same result, that's better evidence. If you can vary different conditions, if you can predict some of the lurking variables in very different conditions, that can give you stronger evidence. I always think about this one more in terms of medicine, but higher doses associated with stronger responses, then that's more evidence that you might have causation. And kind of like with the firefighter example, it has to make sense, and your cause has to precede the effect in time, otherwise it just doesn't make sense.